He lives in the rainforest in Costa Rica. He's transparent. He's made out of kind of silicone gelatin-like material, biogel. He can only actually live under shade in shaded areas. If he was in the sun, if he was nearby, he would be dead because of UV. But I think looking at this thing makes me think of a whole new type of architecture, which is made out of composites, where you begin to have abilities for gradients of color, of transparency, of being able to see through things, which I think is very exciting. And at the same time, matched with that is a huge revolution going on right now in 3D printing, which is something that I've personally been involved in. This thing on the left, this was printed by an Objet 500 printer, which is a company out of the Middle East, actually. And they now have a bed about this size, which can print in 7 different materials with different rigidities. You can print in color, you can print gradations of color, gradations of transparency and opacity, and gradations of rigidity. So you can combine rubber with hard plastic, right? So, I mean, this stuff is already being used in aerospace and in automobile and naval design, but in architecture, obviously, there's a scale issue. Scaling this kind of work up is currently a problem. But to me, it fits perfectly with the paradigm of thinking about composites, of thinking about multi-materiality, and of beginning to grade and mutate materials. So ornament, as I brought up before, and the reason why I call it the problem with ornament is that, I have a bit of a problem with that word in general, because ornament tends to be used in a way where it's always considered to be excess. I think maybe decoration is a better word for excess, but even decoration is never really excess. When it appears in architecture, I think it's part of, it's critical. It's never that which is applied to. It's always very important, both culturally and formally, and a lot of different levels. So I have kind of an issue of the word ornament. I use it myself a lot because there isn't really a better one. I guess I need to make up a word for that. But it's something that I think is critical for the understanding of architecture. I don't think it's excess, as a lot of modern architects would have you believe that ornament is outside of architecture, that it's excess, that it can be cut off of architecture. I don't believe that. So form and function, interesting. So a couple more animals, and then I'll show you some projects. Especially rainforest animals. I mean, they're just amazing. I'm just amazed by these guys. So this keel-billed toucan. I mean, this thing is ridiculous, right? Why does an animal need this beak? It doesn't even look like it can stand up straight and fly. And it was taken for granted by scientists, even until very, very recently, that the beak was just a matter of sexual selection, meaning that it was a kind of identification of males by females. So it was very colorful and very large, and it was just assumed that because that's been seen before in other species in nature, that's the reason that it exists like that. But then it turns out that it's not that. It turns out, after more research of these guys, in particular in flight, and in particular through thermal imaging and other types of analysis of this bird, they realized that although, yes, the color and the size may be related to the reproductive angle of the bird, that it also has been co-opted over time as a gigantic thermoregulator for the bird. So they noticed that when it's flying especially, that all the heat is getting exhausted through a fine network of little capillaries in the nose. So it's actually a gigantic radiator for the bird. So, you know, you can't really separate that any longer. The form of the beak, the color of the beak, the signifying aspect of the beak, but also the underlying performance of the beak. So what is ornament and what is performance? Those things get mixed up. So, also in architecture, you know, looking at early Roman architecture, where they were beginning to try to figure out how to move beyond the very simple idea of an edifice with columns and beginning to create enclosure by putting a wall halfway through the column. So these are actually these are called engaged columns, meaning that they're engaged in the wall. But the interesting thing is it automatically brings up the confusing issue of what is actually structural here. Are the columns holding up the roof, and this is just an infill brick wall? Or are the bricks structural, and these are decorative here? In this building, we know for a fact that these are in fact engaged columns, and they are holding up the roof, and that this is an infill wall. But later on, and into the Renaissance later on, you begin to see columns become pilasters. And a pilaster is an ornament, and no longer structural necessarily. It depends on the building. So I think that this is sort of the beginning, to me, this is sort of the birth of the pilaster, although I don't think the Romans identified it as such. The birth of the possibility of creating a nuanced relationship between that which is structural and that which is ornamental, which I think is very important moment in time. And you know, later on, Hector Guimard, working in France in the Art Nouveau period, much later, of course, in the early 20th century, beginning to carve stone in certain ways in order to enhance things. In this case, very interesting to me, enhancing an aperture, an opening or an entry into a building, and beginning to enhance that through this kind of intricate sculptural quality. So this thing, we have a pretty good idea that it's not structural, but it's still functioning. It's still quite important for the overall building design. You couldn't just remove it. It's actually leading you in and emphasizing the entry of the building. I'll get to tattoos in a minute. Another animal. I thought we were done with the animals. So, what I want to say about this guy, this is called a, is this the biology department? Am I in the wrong place? Yeah, this is a building. No, it's not a building. Listen, I mean, in all seriousness, there is a huge difference between biology and architecture. And although, you know, I find it highly inspirational, I'm not necessarily interested in making buildings that look like animals. I don't think that's very productive. But I do think there's a lot to learn from biology because of the sophistication, frankly, of creatures, the sophistication that's happened over a long period of time. Like this guy, why am I interested in this? It's because of the loose relationship between the features, the color and pattern features, versus the form of the fish. Okay, so in some areas, like we can imagine what's going on here. You have the tail with some cartilage in it that gives it some structure, and you have some striping that's sort of emphasizing that, right? And that's also going on down here. But then you look over here, and then suddenly there are stripes. And the stripes don't seem to be emphasizing anything to do with the underlying structure of the fish. They're completely free form. And then there are other areas where suddenly there are polka dots and things going on, which are a complete hybrid of the striping. So I think it's very, very interesting because there are other factors at play. There's something to do with its predators. There's something to do with camouflage. There are lots of other issues going on, but some of it's emphasizing the underlying form and some of it's not. And this is why, and I'll talk about tattoos in a minute and why I'm interested in that, because tattoos also tend to do one of two things: either signify and get stamped onto a body, or emphasize underlying formal features. One of the two, or both. I think I won't talk about computation right now. Off track a little bit. There's a tattoo. We've been making a lot of tattoos in the office lately, computational tattoos. Maybe I will just say one word about this. I'm really, all of my work is based on a computer. Actually, that's not well said. I want to say that I use the computer, but my work is not auto-generated. And if any of you were following that whole discussion about auto-generative work versus, let's say, craft, there's a big discussion going on about that in the architectural discipline of how to use the computer and to what degree you're using it in a willful way as an artist versus you're actually acting like a scientist and trying to compute something. So this is my drawing of tattoos using the computer and using the power and the computation that you get from using the computer, but also having some willfulness and intuition embedded within it, embedded in the technique of actually making these things. is my main interest right now. In other words, I'm trying to mess up, this is why I call it messy computation, I'm trying to mess up the cleanliness that you see in a lot of schools, in particular in the East Coast of the US, but also in a lot of Central Europe. There's a kind of purism that's going on now about computation, which is like I input this kind of information, weather data, sun position, type of material, width of panel, put it all in there, and then I get out the back end the perfect architecture. And I think that's not only not possible, and a kind of a legend that that's possible, but I find it really unproductive. And I'm much more interested in the way that architects can also sort of individuate their work and use their intuition. So, okay, so now I have some projects classified. I've been classifying lately, trying to consolidate and classify. So these are the DLAM, ducts, and pleat projects. I may just show a couple and skip through it so I don't get alarmed. This is a prototype that we did some years ago, which actually I recently identified as the beginning of the tattoo projects. But it's the idea of this prototype and other prototypes that we've done in the office is that they're not a piece of a building that exists, but they literally are a piece of a building that could exist. And they have certain features in them that you could use to design a building. Okay, so this isn't a detail of a building design. This is a prototype, a forward-looking prototype that could possibly be used to design a building. And in some cases, we have made the prototype and then done a building based on it. So this is called which one is this? This is thermostrut, and basically the idea was to have a composite structure which would begin to have pleats in it to gain rigidity. Those pleats would go from linear elements into a more cellular kind of area where they could begin to create apertures or windows. And then this whole thing is inlaid in here, here, and here with solar thermal, which basically, as you know, is like how you would heat a swimming pool, especially in an arid climate like this. You can run coils, black coils on the roof of your building and basically heat water. Okay, so that's one really low-tech sustainability measure that I think is important for architecture to use because it is so low-tech. But you tend to see it as engineers would do it, which is the most optimal way of coiling black tubes, putting them in prefabricated panels, stacking them on the roof, and that's your system. In this case, I'm trying to customize it and beginning to fuse an architectural agenda with an engineering agenda. And so we begin to have these coils of tubes, which are still coils, and they're still endless as they need to be. Heating and cooling, basically producing hot water for the use of the building. And in addition, there are these kind of pockets which are pushed down, which can collect rainwater, so you can use the rainwater for a gray water system for the building as well. So, and in addition to all of that, you have some color gradients which we're beginning to bring to the fore or to the back different features of this. So again, this is similar to the blood-comb jellyfish. There, you can't really peel the systems off of the architecture. It's all one whole. This is another one. It's a prototype. This one's actually called gray water panel. It has a similar idea for the gray water collection. It has channels in it, which can begin to collect rainwater, which are also the water is also collected by these pleats, which are sticking out. The pleats are also one continuous loop, and the idea is that it's a one continuous loop of algae. And I don't know if anybody's familiar with algae photobioreactors, but that's another really interesting sustainable biofuel that's just now getting integrated into architectural surfaces, where you take a transparent tube, you fill it with algae, really standard algae colonies, although it's getting engineered now, and you expose it to the sun, and you feed it some carbon dioxide, and it basically produces a kind of biofuel that you could then use to operate, let's say, any number of types of machinery or whatever for a building. So this is the kind of thing where, again, in the next 10 years, as it begins to get optimized by certain companies, I think you'll find it on building facades and building roofs, And it'll start to, in combination with other measures, you'll also start to be able to take your building off the grid better. And of course, you can't separate what is ornamental and what is doing work here. This guy is, this guy's called Batwing, and came from an interest also of getting rid of hardware and fixtures in architecture, especially in ceilings. It's something that, if anybody's ever designed a ceiling in here, you know how complex it is with all of the fixtures and the sprinklers, the lighting, the air systems. There's not even that much in this particular ceiling. Usually more stuff, fire alarms. There tends to be a big collection of hardware, of stuff that seems like it's from the wrong era, in my opinion. So Batwing is a prototype that's trying to deal with fusing some of those things together, things especially like heating and cooling, ventilation, and lighting, and trying to do it in a way which is much more smooth. So this is a piece, you could imagine a piece of a wall or a piece of a ceiling. And it's got lighting. This is a very early one, actually. This one was done almost 5 years ago. But the idea is that you could use surface to armature geometry and begin to delaminate surfaces so that you can run air through them, and also have lighting embedded in this whole thing as well, so you can begin to trace some of the dynamic flows of air running through the space as light. But also that you would you'd supply air at room temperature to this thing, rather than trying to heat or cool it at a central air conditioning place at room temperature, and then the air is heated or cooled through a radiant system, which basically means hot or cool water is running through these microcapillaries, so that when the air gets near the space before it's thrown into the room, it gets heated or cooled locally, which is a very, very good way to do it. So there you see some of those little microcapillaries. There they are. Microcapillaries are an existing technology. You'll find them actually in ceiling panels now. It's this little blue plastic tube. It's usually for cooling because it's above your head, so it cools, it falls down in the room. But this is, again, me taking an existing technology and then kind of pushing it to see what could it be if an architect got his hands on it, and what could it be in terms of creating space and atmospheric effects. This is my office, and this is a prototype that we made. We had this done in China, actually. It really is just a prototype, though. It's not made out of maybe appropriate materials. It's made out of giant blocks of recycled ABS plastic. It's all milled in China. But it was a really nice piece to make. It also was one of the first times we started talking about what I call meta seams, which are these seams embedded in this piece, which really have nothing to do with panelization in the sense of defining material limits and edges based on industrial capacities, but actually starting to use seams, because we're in the world of composites here, defining seams in a much more free form and almost ornamental way. Another piece of that. This is a giant piece for our show. Project based on Batwing. This thing's going on at the same time as the Batwing prototype. We decided for a tower in Guiyang, which is a 110-meter tower, office tower in Guiyang, China. This one was actually done with MAD architects together as part of a master plan. This is their building, actually. This is Yansan Ma's building right here. So this project was based on Batwing. The idea was to remove all of the mechanical systems from usually at the center of the tower, put them on the exterior, and begin to use it not only for heating and ventilation, but for lighting and also for taking care of the lateral load of the building. This is an earthquake zone. So here are two buildings kind of relating, talking to each other. And here you see a conventional heating ventilation system. Not very interesting. A lot of sheet metal, risers, ducts, and on the top you have your cooling towers for exhausting heat. The model that I'm talking about here is when you begin to exteriorize all the mechanical systems and stiffen them, you get a giant lateral frame, and then taking the coils which are up inside of those guys, up inside of those cooling towers, and unwind them into kind of a skin. A skin that runs across the whole tower, which can constantly exhaust heat, like a skin of an animal would. Here you see the heat being exhausted through these giant ducts going up. So you're getting a stack effect, basically, where hot air draws itself up and creates it. Without fans, it's just exhausting its own heat. And structurally, the inside, this is a plan. Structurally, these ducts are fiberglass inside of here, so they can be lit from the inside, and then structural precast elements out of concrete on the inside, so these are the columns running all the way up, and then a skin on the inside. Okay. This project was a piece of public art which was never built. Even though I won a competition for it. It's on Flower Street in downtown Los Angeles. Very small project. It's one of those projects where in the States you have to spend 1% of your construction budget for public art, which, you know, architects usually hate that. But now you're finding, because the economy is not so great in the States, that architects are competing for these 1% projects. So I got drawn into this one, and the weird thing about it is that there's not really any space to put public art at all. In fact, there's the building coming down and the sidewalk, but they're renovating, so they need to spend their 1%. So it was a strange project. We couldn't really find a site, so we decided to do a bioreactor for it, which basically becomes a kind of aquarium which is embedded into the wall. There was really nowhere else to put it. It's a two-part piece, however. There's a bioreactor, again using algae, as I mentioned before, over here, which runs 24 hours a day. So it's got embedded lighting in it, and so that it can constantly photosynthesize, whether or not there's sunlight or whether or not it's the middle of the night. You can use artificial or natural light. The algae don't care. So that's the one element, and then during the day we've got these things which we call the tree monkeys, which are basically solar panels which are winding up this tree next door and sticking out and collecting energy during the day to run the lights. So it should be a closed loop, and it should be producing biofuel for the building. This is the first of two projects that I did with a company called Virgin Oil in Los Angeles. They're really cutting edge, state-of-the-art biofuel company. They're working on engineered algae right now, a lot of different applications. And I found out about them when I was looking into luminescent technologies, and then found out that they were in fact working on the same subject I was, putting vats of algae down in the basement of houses and having these 24-hour LED lighting systems, which would basically be creating biofuel on a 24-hour cycle. So I worked with them on this project, and that was pretty exciting because I love the luminescence and the beauty of their systems, and they were the engineers, and we could kind of see together how we could work and make something sort of beyond engineering and architecture. So there it is during the daytime. My videos aren't going to work today. I don't know why. So this is one more bioreactor project in Perth. This was a competition for another piece of public art. These guys were more volumetric, less of an aquarium. Actually, they were still aquariums, but it was a swarm of aquariums in a public plaza in Perth, Australia. And these guys were based also on a technology from Virgin Oil. This is actually the precursor to Flower Street, when they were still using fluorescent tubes embedded in algae before the LED control systems came out. But it didn't matter. So we basically embedded these coils inside of these polycarbonate containers, which also are creating biofuel, and they're embedded in the ground. So this is the technology on the left. It's kind of spindle with fluorescence on it. I wish I could show my also early interest in some articulation going on here, which is related to solar transducers, which is a transparent solar panel. Beginning again to figure out how the feed for those things is starting to be articulated architecturally, almost as tattoos. So this is another early project we started getting into that. And no video. I like this one. Sorry.
First one.
There you go. I just want to see the other one. I like this one too. This is sped up. This would be the cycle of whole night, like fireflies at night. It tunes, it has a controller that tunes what the algae needs over time. So you get different colors and different intensities of light based on what the colony needs to survive. So. Okay, so, Jihad, how am I doing on time? How much?
20 minutes more.
Okay, thank you, that's all. So maybe let me show you a car. Yeah, so back to this issue of multi-materiality, and again, you see these things in nature that are just, like, look at this thing. This exists. This is called a barrel-eyed fish. The funny thing about the barrel-eyed fish is that these are not eyes. Those are its eyes. Right? It's looking for predators which are up above it. So it's looking up. These are its nose. It's olfactory organ. But that's not even the reason why I'm showing it. The reason why I'm showing it is because look at this material. What is this material that goes from opaque to transparent, right, in a gradient? It's amazing, right? It's a biocomposite. It's quite amazing. Again, related to that discussion that I had before about multi-materiality and it being sort of on the edge of engaging architecture. On the left, you have a shark skeleton. And if anybody has looked into, I love sharks, and the interesting thing about sharks, and one of the reasons why they're such good killers and they're so robust in a fight, is that they don't have bones. They look like bones, but they're all cartilage, all cartilage. And if you look also at the way the cartilage is distributed, sometimes it's in sort of linear elements, like obviously this is kind of spine and other linear elements, but sometimes it's platelets and things which are verging on skin, but they have some rigidity to them, like your nose, the cartilage in your nose. So thinking about those things, I was asked by Renault to do a car, with a kind of futuristic car. But we weren't looking at, because I'm not an engineer, I was not looking at the drivetrain, in other words, the engine or anything like that, because I'm not, that's not what I do. We mostly looked at the skin of the car and tried to figure out, we looked at the chassis and the skin of the car to figure out how those probably could contribute to that discussion, as something that we know a little bit about. So looking at the history of the car, You have the ladder chassis at the top, which is like trucks usually have that. You set the body on top of the ladder, and it's basically its own element. You can set any number, like buses have those, trucks have those. You have the unibody, which is almost all economy cars in the world are made unibody currently. Very complex to make because you have to do a lot of metal molding, but very strong, and there's no underlying frame. So this is monocoque structure, equal skin, very economical and lightweight. Then you have a space frame, which looks very old actually, because some early cars like Jags and things like that had a space frame, but also is still being used for supercars, like that happens to be the chassis of a Lamborghini. So the space frame is still another lightweight way to get a lot of stiffness, especially for crashes. So that's sort of where we are with car technology in that zone. All mineral materials, okay? Minerals meaning iron-based and aluminum-based materials. And here's how the auto manufacturers kind of look at softness or crashes or whatever. Like on the left, you see how the unibody is basically constructed. It's a three-part. Sorry, this is so unreadable. But a unibody car is a three-part system. It's the front of the car, it's the cabin, and the back of the car. And the front and the back are considered to be disposable. So in case of an accident, they're assumed that they'll be crushed and the cabin survives. That's the basic idea behind a unibody, so I think that's interesting. Another thing that's interesting is the idea of airbags and pneumatics in cars. This one in particular I find absurdly funny from Ford Motors. This is they discovered that a lot of pedestrians were getting mowed down by SUVs, and so they put exterior airbags on this Explorer so that, you know, if you get hit by the car, you bounce off. And then this was sort of, I mean, to me, just as a designer, I look at this and see, like, what were they thinking? You know, it's like there's no integration. I don't, you know, it just there's no rethinking maybe of the hood or even of the front of the car at all. You just add these airbags. So anyway, I took that as a provocation, I guess. And so the car that we started with the idea was to deal with polymers and silicon gels and materials which can range from very soft to semi-rigid to quite rigid, but on a gradient. So this car is intended to be 3D printed. Right now, you'd have to print it in about 16 parts, but and figure out how to fuse the parts together. But that's not impossible to think about. So this was an idea. One thing you could, you know, and this part of the car is not worked out, but one thing that you could do is start to imagine that airbags are in fact embedded within delaminating skins. They become part of the skin, and then you can put air or fluids or whatever you want to do within the skin, and then let it, you know, in case a pedestrian hits it, you bounce off of it. So here's the chassis of the car, in air quotes, because really the skins are structural, and there are some elements which are armature-like, and other elements which are surface-like. So here, it's a synthetic cartilage, which is then grading back into elements which might be a little bit stiffer, including the seats and other things, so that you get a gradation between what's stiff and what's soft, based on the structural engineering of the car, rather than a kind of universal metal. So here's a gel then that we used with microfibers in it. It's almost like silicone, but a gel that we kind of wrap the whole thing in. So this is it's as if the cartilage was wrapped inside of this rubbery skin. So this is the actual outer and very aerodynamic skin of the car. And you see here how it's multi-material, how embedded within the silicone, you start to see the cartilage areas which are inside of it and creating rigidity wherever it is. A lot of engineering tools now, especially ANSYS, are capable of doing relatively quickly surface-based analysis rather than vector-based analysis, which is also something that I think is critical in that transformation from vector structure, like sticks and beams and space frames, into surface-based structures like monocoques, like ship hulls and airplanes and those kinds of things. Oh no! No video. Sorry, I got this bullshit. So embedded embedded within the softness, we have this system of actuators, which are almost like ligaments, which are inside of the doors, so that you can begin to, rather than opening a door with a hinge, suddenly the whole car becomes a kind of living hinge, so that everything's flexible and movable, but of course you have to trigger that movement somehow, so it has some kind of ligaments or tendons embedded in it that can be actuated or triggered and begin to have openings for doors or other kinds of things. So yeah, everything's soft, there's no hinge. You even get this little, my favorite part of this is this little vibration here. It's almost like a shuddering. I'll show one last video here. This is my favorite one actually from the car. What is this? This is a way of thinking about how a car which is semi-rigid could be rolled up almost like a tent, rolled up and put in a box and shipped from the point of its manufacture to where you actually buy it, rather than just these endless shipping containers, cargo ships filled with cars being delivered. You actually roll it up and deliver it. So embedded in the skins of the car are also these volumetric elements, which start to, as I said, some of them could be filled with air or whatever for certain reasons, but others of them could also be an algae bioreactor, which we began to embed in the surfaces as almost bladders or big lumpy volumes inside the surface. There's the car where you see kind of everything coming together, the actuators, the bioreactor, and all that. And there's a wheel which we also designed as one 3D print. If you don't no longer need to have the difference between the material of the rim and the rubber of the tire, because the multi-material printer, you just print it in one pass, all the different material qualities, and it's a mono wheel like that, which, if you ever needed a replacement, you just 3D print it in one. Okay. Well, this is a project that I did with my students a year ago, and I thought you might be interested in it. It's based on composites, so it's a monocoque structure, all surface structure, no internal framing. And we worked on it for a long time in the sense of trying to get beyond the idea of the way that fiberglass is currently used, like with in surfboard construction, you basically make a big foam mold and then you just fiberglass it in order to stiffen it, right? You put the fiberglass on the outside where it's doing the most work, and your mold is lost, meaning it's inside there still, and you basically get a stiff surfboard. What we wanted to do is have more heterogeneity in the thing, and so we started to think about tape and how we could begin, literally by using carbon fiber or fiberglass tape, begin to add a hierarchy to the structure. So we have zones of more relative stiffness and zones of less stiffness. Okay, so that was the basis of the project. We did a bunch of studies, but through the ANSYS, if you look at some of the early analysis of it, this is assuming everything's 1/8 inch fiberglass. We started to look at these stress areas and convert those into areas of tape where we would build up the surface up to a 1/4 inch thick. So this is 1/4 inch and this is 1/8 inch, and then there are all different gradients in between of how many layers of tape you actually use. Oh, my videos. The nice thing is that we started using painting tools to make this project. So we're actually painting structure on the surface, which is something that's immensely interesting to me. Because as I mentioned before, there's a willfulness of the designer implied through painting, but at the same time we're painting towards an engineering goal. So here's all the tape once you subtract out the things that are not taped, and it gets pretty interesting. Also how you make components in composite construction. There's no longer hardware or clips or bolts. You basically peel it or you fuse things together. This is a mock-up of the piece. We're using actual duct tape, just the layout where the tape was for the manufacturer. Here's the layer of orange tape going on there. We just dyed it with shoe dye because we wanted it to stand out. So, and be readable as structural tattoos. Here's the piece installed. It's a 50-foot cantilever, very, very lightweight, and there it is flying above your head. This is installed actually inside the school. So you can see here, this is something you could not do with a different material. It's extremely lightweight, and it's all skin. There's no structure inside. Okay, here's a piece, which is another piece of public art, which took on the same idea of structural painting. This was for a project in anthropology. And we wanted to not only use a thin material like tape as structure. So let's say using structural tape for ornamental, but also engineering ends. But we thought in this case we would also embed other kinds of thin film technology like solar thin film on the left, electroluminescent lighting on the right, all of which is very, very thin. So this is an ongoing interest of mine to kind of compress and squish things together where you get structure, envelope, lighting, and solar systems all within something this thin. So here's the piece, and I'm going to show you the process that is at night. You can see that there's the melon areas are the OLED lighting. The black areas are composite, which are doing most of the structural work. The black areas are also embedded with solar panels to run the lighting. And again, we use surface structural analysis from ANSYS to begin to get a structural diagram that we could use inside of the paint program. So we wrote a software to bring the actual color information from the engineering software from ANSYS to bring it into a paint program, which is called ZBrush, that we're using, so that we would have that information inside of it. So here's I'll just show I'll show two more projects and we'll be done. Don't worry. Here's us in the painting software beginning to use the structural data, but also beginning to alter it by hand in the areas which are not critical. In other words, not destroying the structural diagram, but beginning to alter it for aesthetic reasons. So because we wanted to. This is one study. No. This is the final study. It basically follows the patchwork from the structural analysis tool, where the purple is the stuff under the greatest stress, so we left that as a composite, and on the black areas for solar. And we wanted to break down the zones between the transparent polycarbonate and the opaque areas with this kind of loopy leopard pattern, which we identified along the process. And so there it is. You see there's this loopiness which breaks down the areas between what's opaque and what's transparent. Here's another project going on at the same time. This is a prototype similar to Batwing, except this thing again is about squished surfaces where you're taking OLED, thin film solar, and composites, and in this case I wanted to create an aquarium effect where you'd be looking through a giant aperture at something on the interior. And the interesting thing about it is that this is all made with one surface. So imagine this is one surface which involutes on itself. You're looking through the surface at the surface. So it's all super thin. It appears to be volumetric, but it's in fact made out of a single surface. So there it is. You see lighting embedded in it. It's different pattern logics too. The solar is identified with a kind of spotty pattern, whereas the lighting is identified with stripes. So this is a hybrid of a tiger and a leopard. I think I want to show. I'll show a much older project where we started getting interested in vacuum forming, which is related to the workshop that we're going to do. This is a project that was built in New York City for the PS1 program there. If you don't know what that is, it's basically, PS1 is basically the contemporary art wing of the Museum of Modern Art in New York. And every summer they build a pavilion out in their backyard, which is a big public competition. And we won that in 2003, so this is pretty old. But I still like this project. Basically, the idea was to create a long span structure. The thing's 150 feet long, 50 meters long, and do it not by having a hierarchical structure, but by having volumes nested within a loose outer skin. So these giant diamonds are structural volumes around which there's a second skin wrapped. So the structural volumes are wrapped in skin, and then the outer skin, which is a shade structure, is also wrapped in skin. So you can read simultaneously structure as volume, and then and as skin, and then skin wrapping all of those things together. So here's a picture of it under construction, where you begin to see that there are these volumes which are vacuum sucked almost from the top to the bottom. And they're readable as volumes, and they're structural as well. So, and then there it is in the daytime. Reads completely differently. It reads as a shade structure, and you don't read so strongly the volumes on the interior. You read it as all skin, which is quite nice. The skin is based on very simple conoidal and hyperbolic geometry, so lofting paraboloids and straight line segments, so that you get some curvature but not too much, which works really well with the material that we use, aluminum, expanded aluminum. Some of the documents used, so you can see the whole belly and the roof of this thing is based on warped surfaces, which keeps the material from hanging down and keeps it stiff. This is one of the events. And there it is from the structural cells. A video. I'm going to skip.
Some projects in China.
Yep. We show one project.
الله يحل شغله بس روح
Very quickly, this is a competition for an opera in Busan, Korea, and it's a very strange site. It's in the middle of a man-made island, so there's going to be a whole development on there, but this is the kickoff for that development. This is where we were working on this idea of an implied outer shell, which I mentioned before. So basically, it's a figure or some kind of a building with then almost a secondary building around it, which implies enclosure, but isn't actually enclosed. So it begins to create indoor-outdoor space, public space, which is enclosed within this implied outer shell. So here's some examples that we were looking at, things like, in the case of the dragon and the skull, how the wings of the dragon begin to imply an enclosure and create shade, but the building itself is actually pulled back from that. Other examples of giant figural apertures in this case, or in this case, something which is, this is from Star Trek, something which is all outer shell and has no middle at all. So I'm calling that the missing middle, or all skin project. All of which I'm very interested in working on different projects. So here you go, this is what an implied outer shell project looks like. One nice thing about that is it creates a lot of shade, so you have a really nice entry sequence where you're kind of transitioning slowly, almost like a curtain going up before performance. You're transitioning slowly into the buffer zone, which is protected from the monsoons and the sun before you go in the building, and it's a public square. So there's the project. This time tattoos as articulation are being used to organize apertures or openings in the skin, so they're not just punch holes in it, but they're actually part of a chain. And here it is, on the inside there are two theaters in this project, actually one major theater and one minor theater, which you can imagine are almost tucked in between two skins. So there's an inner skin and an outer skin. They're tucked in there, and then the space in between becomes the public plaza. show you the Chinese projects, and we will call it a day. I'm actually working right now on a really exciting project with Tom Main from Morphosis and Neil Benari and a few other LA architects. We made a joint design team, and we're competing now for a university in China, which is the most important thing that I'm working on right now. And that's really exciting to work in a joint design team. I like that very much. Here we go. China. Hold on, how do I get this to work? Okay, so, yeah, the reason why I'm showing this image, okay. First of all, this is my partner in China. He's a great guy, Director Zhang of LDI, which is Local Design Institute, of course. And you've always got to work, when you're working in China, you always have to work with LDI in China. At least 50% of the services have to be done by them. But you would work with them anyway, you would work with an executive architect, because you need to have political clout and you have to have friends there in order for anything to go forward. So this was an important day for us because we had just won a couple of competitions for sports projects, where, however, this is a different, this is a funny image for me because this is us at the groundbreaking for a hotel project, which I'll show you in a second, where they're breaking ground, but this is the first time I've heard of the project or seen the site. So I'm brought as the architect of the project to the groundbreaking. I have no idea what's going on. I had flown in the day before, and I'm standing making a speech at the groundbreaking for the hotel, having not designed the project yet, but they're starting the foundation. So, I mean, of course you guys know about that. Here in Dubai, that goes on all the time. But, Ajman, that was kind of shocking and funny for me, and so I remember this day very well. But let me show you this competition for a sports project in Shenyang, China, which is a big project. It's 123,000 square meters, which, you know, a young guy like me would, you know, never anywhere else in the world maybe except in China be entrusted with. So that's very exciting to be able to go somewhere and have them give you a chance. It's, the site is here in this area. It's a central city block in the city of Shenyang, which is north of Beijing. It's a city of 8 million, so it's not a village, it's a big city, and it's a major sports project. Our design is really in two parts. It's a sports rec center, which is a massive building here, built almost like a parking garage, very inexpensive, so that we can save all the money and put it into an icon building that they asked for, which has huge apertures. One of them, huge urban windows, which are looking out at sports, but also looking back out at the park to the left. And that building houses a bunch of indoor sports,